So example 6, we have a piecewise function. So the first thing we're going to do in a piecewise function is just to check for continuity. So at x equals 1, we're going to plug 1 into the green part of the graph and get a value. And then we're going to plug 1 into the red part of the graph and get a value and see if those values match. So when I plug 1 in, I'm going to get 0 in the green part. I can show that using a limit. From the negative side, I'm going to use the green equation, x cubed minus 1, and I get a y value of 0. Okay, if I plug it into the red part, I get 1 minus 2 squared minus 1 again is 0, and I'm going to show that formally using the red limit. I plug that in, x equals 1, I get y equals 0. So that is a coordinate on my graph, and it is a point of continuity. So it's defined from the right hand side. The actual equals is on this part. So I'm just going to write this as x is 1, y is 0. So that's going to be one point on the graph. Okay. In fact, that is the point where the two graphs meet. So we can say, based on these two limits, that it is continuous. Okay, so left and right side limits are the same, and the point is defined at the coordinate x equals 1, and it's the same as what we have in our limits. Okay, so we have passes continuity. We want to find the zeros of this, so let's find some zeros here. So for the green part, when x is x minus 3, x cubed minus 1 equals 0, x is equal to 1, so it hits the 0 at 1. And for the parabola part, we need to solve x squared minus 2 squared minus 1 equals 0. So we end up with x minus 1 minus 2 squared equals 1. X minus 2 equals plus minus 1. So we get x is equal to, well, we already have the positive 1, but we also have a 0 at positive 3. Okay, so it's going to cross the x-axis at 3. So at 3 and 0, I know I have a vertex in there, so I'm going to leave a bit of space here. So at 3 and 0, I have another 0. Okay, so these are my zeros. I'm just going to block this off here. This is calculating my zeros. Okay, and I can also do my limits and endpoint behavior, but I know my cubic function is going to go down to infinity, and I know my quadratic function is going to go up to infinity. So I'm not going to worry too much about that. I'm going to then now do my derivative. So I want to find my derivative for this, because I want to see if I can find some min and max points. So f prime of x, when I differentiate the green part, okay, I'm going to end up with 3x squared for x is less than 1. And for this part here, I'm going to end up with 2, the linear function 2x minus 4. This is for x is greater than or equal to 1. Okay, so then I have a 0 slope at x is 0. Okay, so my f prime graph, I have a 0 slope at 0. And then from the other part of the graph at x equals 2, okay, I'm going to have another 0 slope. Those are going to be points that I have to test. So at x equals 2, okay, at x equals 2, I'm going to plug in my coordinate at x equals 2, y equals negative 1. Okay, so that's going to be the vertex of the parabola. And it is a min point. Just showing my slope tests then. Plugging in my slope. So f prime at negative 1, I'm going to plug it into that equation there. It's positive, so I know it's going to go up. I have 0 slope here. And then f prime at positive 1 also gives me positive. So this looks like it is a slide to that point. And then I have this point. Oh, I forgot to label this point here, but we have to consider our point of where we have where the two graphs join at x equals 1. Okay, so we need to know what's happening there. And at x equals 2, I have 0 slope here. Okay, now I can kind of see that's the minimum point. So it's going to draw it like that, but we should evaluate what's going on at 1. So at x equals 1, we have to figure out what's happening with the slope. So I'm going to have to do a limit here because I have to test the slope from the right-hand side and test the slope from the left-hand side. So limit as x approaches 1 from the negative side. Okay, from the negative side, it's going to be my green function. So I'm going to just make sure I color that in green. So from the negative side, I want to know what the slope is. And the slope is equal to positive 3. Okay, so it's positive. I can see that from my slope chart that it's approaching positive 3. But I also have to check that my limit for my slope is the same from the other side because I got to figure out what's going on at that point. So from the positive side, I'm checking the slope in the equation, in that equation. And when I put 1 into that equation, I'm going to get a slope of negative 2. So because the slopes are not the same from the left and right-hand side, okay, the limit of, and this conclusion is going to be the limit as x approaches 1 from both sides of f prime of x does not exist. Okay, so then we have to be aware that something can happen across that coordinate. So we have, I'm going to test the slope, get another slope point on the other side. So at f prime of 1.5, testing it into my graph, I'm going to end up with a negative slope here. So across that point, I have a negative slope. That's a minimum. That looks like that's the case based on my coordinates. I'm also going to test the slope at x equals 3. So I want to test on both sides of that 0. At x equals 3, my slope is now going to be positive. So it's going to be going up. So there's my slope chart. I have undefined slope at 1. I know that it's got a positive slope coming into it, negative slope coming out of it. It is a kink in the graph. Okay, so I'm going to start putting in some few more coordinates here. So at x equals, let's put in 0. At x equals 0, we have a y coordinate of negative 1. Okay, and we know that at 0, negative 1, there, from my slope chart, I can see that there's a slide through that point. So it's going to be a slide through that point like this, and then it's going to hit that point with a slope of 3. But it's going to change slope and to negative, come down through the min point, and then it's going to go keep on going up like this. So that's what my graph is going to look like. Okay, and I could do a second derivative test on this, but again, this one does not ask for a second derivative test.